OK. So thanks for the invitation. All right. So sorry, I'm going to start kind of broad. So you can think of the project as of geometry is sort of the project of classifying complex projective manifolds oh wait, hold on. Actually, before I just jump into it, let me just say. So what I'm going to tell you about is I'm going to talk about some conjectures about the sort of birational properties of Calabi-Yau manifolds that are sort of inspired by homological mirror symmetry. I assume that's why I'm here. And I'm going to first spend the first part of the talk sort of motivating and tell you where these conjectures come from. And then in the second half of the talk, I'm going to tell you about equivariant geometry and how these conjectures and how these have sort of shed new light on these conjectures, really sort of some of the first substantial progress in the last 15 years or so. So, but first I'm going to start with the motivational part. So anyway, so you can think about algebraic geometry as this project is trying to classify all complex projective manifolds up to isomorphism. But that's, of course, like a wild question and totally sort of implausible. So, the next thing that people thought sort of very, very classically is to sort of relax this question a little bit. So rather than classify projective manifolds up to isomorphism, birational geometry, well, we're going to say let's weaken the equivalence relation. And so definition is that two projective manifolds x and x prime are birationally equivalent and I'll write this, say, so birational equivalence is sort of a map like this, written with dotted arrows. If I can find, if there exists algebraic open subsets u inside of x and u prime inside of x prime and an isomorphism. All right, so it turns out that with this relaxation, this is sort of super classical, that this question has a lot more structure. So there are lots of classically studied varieties which aren't isomorphic to projective space, but they're birational to it. And that's a very, that's not me. That's a very useful way to think. So this question actually, unlike the first question, the question of birational geometry admits lots of structure. So you may have heard of the minimal model program and this sort of thing. There are all these interesting ways to try to organize this question. And to try to structure it. So I should say a warning. So, or I don't know I call this a warning. So this question, so this is much weaker. This is clearly much weaker. But still, even some of but still incredibly hard. So this classification of complex manifolds up to birational equivalence is much weaker, but still very hard. And just to sort of give you an example of how that can be, so there's a sort of basic question. So a basic difficult question is does x admit an algebraic coordinate chart? This is the question of whether or not your projective manifold x is sort of birationally equivalent to a projective space. Yeah? And so if you're working in complex geometry, then this is essentially baked into the definition of what a complex manifold is. Every complex manifold has coordinate charts. It has little open pieces, which are isomorphic to open subsets of complex vector space. But in algebraic geometry, these are some of the biggest open problems in the field of birational geometry, is identifying exactly when certain varieties even have coordinate charts in this algebraic sense. So the thing that makes this so hard is that is when you add the word algebraic to these open subsets, basically. So, yeah. OK. So this is a very much easier and more plausible than classifying all projective manifolds, but still quite hard. So I should say that so there is quite a bit of progress, obviously. So the first thing I'm going to talk about is some birational invariants. So classical birational invariants. So because you're on a complex manifold, you have given to you from the geometry the cotangent bundle. So you have a canonical vector bundle, holomorphic vector bundle. Omega 1, this is the cotangent bundle. And this, you can construct from this the canonical bundle, so-called canonical bundle, which is the top exterior power of this holomorphic cotangent bundle. And the first and simplest example of a birational invariant is the so-called plurigenera. So the simplest birational variant is the plurigenera. So this Pn is defined to be equal to the dimension of the space of holomorphic sections holomorphic global sections of the canonical bundle raised to some power for n greater than or equal to 0. And it turns out that this is a birational invariant. This is an invariant under birational equivalence, and it's actually like quite a strong birational invariant. So example, this is, I said that this is a very hard question, determining whether a complex manifold has an algebraic coordinate chart. But these plurigenera, this is enough to distinguish the Fermat quintic, so a famous example in the mirror symmetry community. So the Fermat quintic from P3. Yeah, so so Fermat quintic, this example, this. So the plurigenera are very strong. In fact, if you allow yourself to, instead of working with these numbers, but if you sort of categorify a little bit and work with the vector spaces themselves, so the space of holomorphic sections of this holomorphic line bundle, if you put them together for all n, they form a ring called the canonical ring. There's sort of an obvious kind of product. If you have a section of k to the tensor n, k to the tensor m, you can tensor them to get a section of the higher thing. So in fact, a slightly more, if you just put a little bit more structure, this basically is a complete birational invariant for a fairly large class of varieties. So for varieties of general type, varieties of general type, this ring of is a complete birational invariant. Yeah. So on the one hand, so on the one hand, this is a very strong invariant. But on the other hand, lots of the things that geometers like to study are certainly not invariant. So unfortunately, the cohomology, if I take just the usual cohomology of the variety, or if I take the Hodge numbers, the Hodge cohomology, etc., these are not invariant. Okay, so if you start blowing up a variety, the cohomology gets larger and its Hodge numbers change and all that stuff. At least, yeah, some of the Hodge numbers. So that's sort of the state of affairs. We have some birational invariants, very classical birational invariants, which for certain varieties is basically all you ever need to worry about for this classification problem. But then, on the other hand, there are certain geometric invariants which are certainly not birational invariants. So this is a point in the talk where I'm going to specify now, specialize to the Calabi-Yau situation. So let me just say, just so you know the definition, although this audience certainly knows it, but the definition is that so X will be Calabi-Yau. X is Calabi-Yau if the canonical bundle is trivial. Or in other words, if there's another way to say this, is that there's a global holomorphic volume form. So these names, Calabi and Yau, this comes from the original interest in mathematics. So this is sort of in differential geometry. These are the manifolds that have Kähler metrics with Ricci flat curvature. They're of interest, like lots of examples. So in one dimension, they're the elliptic curves, et cetera, et cetera. Of course, they're interesting from the perspective of mirror symmetry. But I guess the perspective from this talk that I'd like to take is that these are actually just of fundamental interest in birational geometry. And the reason is because, so if you have this condition that the canonical bundle is trivial, this is precisely the worst case for the classical birational invariant. So these plurigenera are all going to be 1 if this canonical bundle is trivial. It tells you no information. So the canonical ring here is a terrible invariant of birational equivalence for Calabi-Yau manifolds. So this is somehow a boundary case. This is a very fascinating from the point of view of birational geometry. So the question is, this beautiful invariant which picks apart everything, and in fact, these plurigenera basically organize the minimal model program. They're the beginning of the entire program of how to classify birational geometry, but in classify manifolds up to birational equivalence. But in this Calabi-Yau case, this program doesn't seem to tell you very much. And so it's really kind of an interesting question of how do you tell apart birational Calabi-Yau manifolds. So enter mirror symmetry. We need better invariants for Calabi-Yau manifolds. So as we're all familiar with, mirror symmetry has led to some really sort of surprising predictions just in classical algebraic geometry. I mean, many of the people in this audience are sort of, you relate to mirror symmetry as a way to take symplectic invariants of a manifold, which are very hard to compute and encode, and to translate them into some statement about some algebraic variety, some mirror variety, which is then presumably much easier to compute with, although that maybe is a matter, that's maybe debatable. But that's like one perspective from the world of symplectic topology, what the use of mirror symmetry is. I'm an algebraic geometer, and from my perspective, mirror symmetry leads to these really surprising predictions. You don't need to know what the mirror is, but it leads to the predictions on the geometry of Calabi-Yau manifolds that come from the philosophy of mirror symmetry without actually having a mirror symmetry theorem. And that's the kind of result that I'm going to be talking about. So what does mirror symmetry do? It predicts the following. So the basic thing that mirror symmetry says is that invariants of a Calabi-Yau X are basically, I'll say, in some sense, invariants of X, certain geometric invariants of X, are determined and are determined by invariants of a mirror, some other Calabi-Yau, X prime. And a piece of the philosophy is that, so in that under this correspondence, deformations of the Kähler class on X, deformations of a Kähler class on X should correspond to deformations in a complex structure on X prime. That's just piece of the mirror symmetry philosophy. So if you sort of interpret this in the most literal way possible, you come to the following prediction, that if X is birationally equivalent to X prime, oh, by the way, from that line forward, everything's Calabi-Yau. So these are all Calabi-Yau. So if X is birational to X prime, then the prediction from mirror symmetry, then the mirror to X, sorry, I called this X prime. Let me call this X mirror. Yeah. Then the mirror to X is a deformation to the mirror of X prime. Meaning that whatever this mirror, this putative mirror is, the mirror of X and the mirror of X prime have the same underlying smooth manifold, which is different complex structures. And so if there's just these two lines on the board, this totally sketchy perspective leads to some really kind of shocking predictions, shocking from the perspective of birational geometry. So this leads to the prediction that the cohomology, so I'll give you two predictions. So in this situation where you have a birational equivalence of Calabi-Yau manifolds, it leads to the prediction one, that the cohomology of X, at least with rational coefficients, should be isomorphic to the cohomology of X prime with rational coefficients. Because I'm saying that somehow the cohomology of X determines the cohomology of the mirror and vice versa. So if the mirrors have the same cohomology, then X and X prime should have the same cohomology. And the other thing is if you read this philosophy, if you push it even further, you could. What?
Do you fix any kind of symplectic form on this derived or not?
Yeah, there's a Kähler class. Yeah, yeah, they're projective. Yeah, I choose a.
There are a lot of.
Yeah. That's true. Yeah.
It depends what is a mirror actually.
Well, the mirror will be a family. Yeah, the mirror will be some family over, some moduli space, which is roughly like the Kähler moduli space of the original variety X. Yeah. So, and the second prediction is that the cohomology of X itself should have mysterious representation. So, like if you look at the versal deformation of this mirror, like this Calabi-Yau exists in some universal family, and the fundamental group of the base of that family will actually act on the cohomology of the fiber. That's a purely classical fact in algebraic geometry. There's so-called monodromy representations. So what this would predict on X, even without knowing its mirror, is that you should get mysterious sort of monodromy representation. So X should carry a monodromy representation of the fundamental group of pi1 of some complexified Kähler moduli space, as they call it. So I just mentioned that now because it'll sort of be relevant in the talk. First, I'm going to talk about this, prediction one. So, but yeah, so in other words, if you go to the mirror and you look at various families that are of complex manifolds which are deformation equivalent to this mirror, you'll get actions of the fundamental group at the base of that family. And under this mirror correspondence, that's supposed to be some complex, that the base of that family, of the mirror family, should be some complexification of the space of Kähler parameters on the original variety X. Okay, this is all like sort of suggestive and pie in the sky, although in some examples I can actually literally write it down for you what it is. And that's what I'll talk about. So a theorem, so
Can you explain how the philosophy leads to prediction one? I'm not sure I follow.
well, the idea is that there's some complexified Kähler moduli space that's a little bit, there's a real part which is actually a Kähler class on the variety X, and there's an imaginary part, and you're just some point that's moving around in some sort of moduli of complexified Kähler parameters. You can imagine there's nothing really that changes on the mirror side if your real part of that Kähler class stops being Kähler on X and switches to a class that's Kähler on some other birational model X prime. So in some sense, you can think of the birational you can think of this birational equivalence as just moderated by a variation of the Kähler structure. And on the other side, so this birational modification is just the two different Kähler parameters, basically. And on the other side, on the mirror side, is two different complex structures.
That explains the philosophy, I understand. But how do you go from the philosophy to prediction 1?
Oh, prediction 1 is just that the cohomology of X is determined and is determined by the cohomology of the mirror. So if two mirrors have the same cohomology, then the two original varieties have the same cohomology.
Okay.
Does that bother you?
Yeah.
Okay. Well, we can talk later, if that bothers you. Anyway, I wasn't expecting this to upset anybody, because this is all from the.
I know that 1 is not true in the sense of rings.
Yeah, that's true. That's correct. Yeah, that's true. Okay, so the theorem is that this prediction 1 holds. And this is due to Batirev and then later Kontsevich and Denef-Lozer. So the theorem is that prediction 1 holds. Namely, if you have any birational equivalent Calabi-Yaus, then the cohomology is the same. And so it's a natural question. So so the proof of this is beautiful but not very geometric. So it's sort of hard to really get your hands on it. It's a natural question to ask. So prediction 1, birational equivalent Calabi-Yaus actually have the isomorphic cohomology. But just to frame this again, this is telling you that even though Calabi-Yaus, even though the standard invariants of birational equivalence for Calabi-Yau manifolds don't tell you very much, actually, luckily, in the case of Calabi-Yaus, you have all these new invariants, like the cohomology groups and the Hodge numbers and that sort of thing. So prediction 1 holds. It also holds on the level of Hodge numbers. So a natural question. Prediction 1 is that a birational equivalent, so birational equivalent Calabi-Yau manifolds of any dimension, yeah. And this is Batirev from around 95. And Denef-Lozer kind of filled in the details. Yeah. Okay, so it's a natural question: is this the shadow of something more geometric? Because the proof of this prediction 1 was actually quite algebraic. It involved sort of point counting and characteristic P was Batirev's proof, and then Kontsevich had a proof using developing basically this method of so-called motivic integration. But basically, they're not incredibly geometric. What do I mean by this is a natural question. So I have the cohomology group of X. And it's equivalent to the cohomology group of this birational thing x prime. But I can think of cohomology itself as a sort of it's like a shadow of some all sorts of geometric objects. So for instance, I can take vector bundles. I can take the category of vector bundles on X, and I can think about the cohomology is some shadow of the category of vector bundles, like Chern characters or something like that. And I could ask, is there some equivalence with the category of vector bundles on X prime? Sort of a dotted arrow. This is kind of a natural question, right? So you can think of cohomology classes as classes of some more geometric cycle theory. And so this is a natural question. So this would be called a categorification. So the natural question is, can you categorify this equivalence? And OK, so the answer to this particular question, can I find a correspondence between vector bundles on X and vector bundles on X prime? The answer is, of course, no. You can look at what this equivalence of cohomology does in some examples, and it just doesn't preserve the Chern. It doesn't take things that are Chern classes of vector bundles on one thing to Chern classes of vector bundles on another. So these, so there's kind of no hope of that. You're sort of forced forced to work instead of working with vector bundles on X and vector bundles on X prime, you're forced to work with complexes. So the answer to this question is just no. There's no sense in which you can directly sort of categorify. But I work with complexes of vector bundles. So I'm going to consider this object that we're all sort of familiar with. But dB of x is the category of complexes of vector bundles. So it's just a slight enlargement of the category of vector bundles. And now this becomes a reasonable question when you work instead of ask if is there some correspondence between vector bundles in X and vector bundles in X prime. Turns out there will be a correspondence between complexes of vector bundles in X and complexes of vector bundles in X prime. And so just another little philosophical point here. I had this as a dotted arrow because I'm a little bit vague about how categories of vector bundles is sort of a categorification of the cohomology. This object here, in my work, I sort of think of it itself as some sort of crazy cohomology theory. Like, what is cohomology? It's something that takes a space and spits out an abelian group. So what is this symbol dB of parentheses? It's something that takes an algebraic variety and spits out some C-linear category. And so I think of dB of x itself as a sort of cohomology theory. And from this dB of x, there are ways to extract. You can extract the sort of rational cohomology of x. Actually, the natural thing is if you can extract the complex cohomology. This is with this Hochschild stuff. You can actually reconstruct more recently. You can reconstruct the topological K-theory spectrum, and then you can construct weirder invariants that are of interest to algebraic geometers, like the algebraic K-theory spectrum. And this one sort of cohomology theory in parentheses is like a one cohomology theory which rules them all. And so proving things about this dB of x leads to sort of statements that decategorify to all kinds of interesting topological invariants. So there's a reason why you might chase this conjecture on the level of derived categories rather than just on the level of cohomology. Yeah. So and also just parenthetically, you can actually recover from this the canonical ring of the variety. So this dB of x remembers some birational data as well. OK, so without, I've sort of been tap dancing around it. But so the main conjecture here is that if you apply, as you all love to do, the mirror symmetry, homological mirror symmetry philosophy, rather than sort of classical mirror symmetry, then that leads to this conjecture of Bundal and Orlov, also from the mid-90s, that if x is if x and x, so given a birational modification of Calabi-Yau's, so any birational equivalence, x to x prime induces an equivalence of derived categories. And this is the so-called de-equivalence conjecture. And it basically follows from the same way. Instead of looking at the cohomology of the mirror family, you look at the Fukaya category of the mirror family. And the Fukaya category is essentially constant in complex families. And that tells you that if the dB of x is supposed to be the Fukaya category of the mirror, but the two different mirrors are just complex deformations of each other, that tells you that dB of x should be equivalent to dB of x prime. So the big result in this direction is a theorem of Bridgeland. From 2000, which says that this conjecture holds so this holds if dimension of x is equal to 3. So basically, this conjecture is just holds full stop in complex dimension 3. OK? And then I should remark that there's sort of this is sort of the most definitive result for compact Calabi-Yau manifolds. They're like shortly after this in the early Bezirkov-Nikov and Kaledin. Did some work, maybe let's say between 03 and 05. So it's known for some. This is known for some non-compact examples. So there's a so-called local version of this conjecture, which is when your x and x prime are actually projective over some singular affine variety. And this is known for so-called sort of non-compact symplectic resolutions. And the method is a very interesting method involving the technique is so-called quantization characteristic P. Unfortunately, it's sort of obstructed, and it only works in the local case. It doesn't really lead to new examples of birational equivalences of compact Calabi-Yaus in higher dimensions.
Can you say something about proof of the original theorem?
Yeah, it's beautiful proof actually. Yeah, I mean he actually constructs it. Yeah, right. Okay. Yeah. The proof is beautiful. Yeah. No. I mean, he actually constructs the birational model, the x prime. Like he studies a single flop, and he constructs the flop as a moduli space of sheaves on the, or not quite sheaves, but a moduli space of sort of perverse coherent sheaves on the original variety x. And then the Fourier-Mukai kernel that implements it is just the universal bundle. Anywho, so this been
But it uses some kind of classification of what
of the flops, yeah. Although actually it's a uniform, the proof is uniform, which is kind of cool. Like the flop, the curve that gets contracted can be quite complicated, but Bridgeland's proof is very uniform. So it doesn't use this sort of complete classification, but it uses that you can factor into these flops that just contract a single curve. OK, so I guess this is this sort of, we've been a little stuck on this for a while. I mean, there are examples, of course. Bundle and Orlov, when they made this conjecture, have examples in higher dimensions of flops of a very specific kind. Like you sort of contract a PN and you replace it with a different PN, or maybe a family of PNs over a smooth thing and you replace it with a different family of PNs. So in specific sort of descriptions of flops, it's known in higher dimensions, but it's been sort of stuck for a while. There hasn't been a lot of new examples of higher dimensional compact Calabi-Yaus for which this conjecture is known. So the theorem that I'm sort of reporting on is that, oh wait, so sorry, I'm not quite, I skipped a line in my notes. OK, so I'm going to tell you about this in a second. So, but the point is that I have to introduce the class of Calabi-Yaus that I want to think about. So what I'm going to do is I'm going to fix a K3 surface. S. So this is our two-dimensional Calabi-Yau manifold. And then what I'm going to consider, I can consider so-called a polarization. So just a class in sort of take a Kähler class in H2 of this K3 surface, and so associated to this, I get the following. I can construct a moduli space. And I'll call this just space M sub H. And what it's going to be is the moduli space of what are called Giesecker H semi-stable coherent sheaves. So basically, you should just think of this as a compactification of the moduli of vector bundles on the original surface S. I'm suppressing in the notation a certain choice of Mukai vector for the experts in the audience, but I'm sort of fixing the topological type of this coherent sheaf, and I get a certain moduli space of so-called semi-stable objects. And the basic idea here is that as H varies, so there's some parameter that the notion of stability depends on, but as H varies, let's say like H goes to H prime, then I get a birational modification, a birational equivalence between the moduli space at H and the moduli space at H prime. This is the basic kind of way. So I just taking a step back, I was like a little bit sort of cavalier about saying, oh, of course, like you just take these examples of birational equivalent Calabi-Yau manifolds. It's actually sort of a hard question if you're not a birational geometer. How do you actually produce examples of birationally equivalent Calabi-Yau manifolds? Of course, like the minimal model program people are fine. That's like totally easy, like no big deal. But this is a nice class of examples where you can literally understand what's going on. This is a compact Calabi-Yau manifold. These moduli spaces. In fact, it's hyperkähler, but that's not actually relevant to our discussion.
You mean to the proof?
It's not relevant to the proof. Yeah. I mean, it's somewhat relevant to the proof, but it's not really relevant to what I want to tell you about the proof. Yeah. So the theorem now is the following. Yeah. So the theorem is that if X is a compact Calabi-Yau, oh, and also the dimension of these can be arbitrarily high. Sorry, I didn't. Yeah. So depending on the Mukai vector that I've suppressed from the notation, these can be very large, very high dimensional. So if X is a projective Calabi-Yau, which is birationally equivalent to one of these varieties, then it's derived equivalent. Okay. So it's sort of the first example of a complete class of Calabi-Yau manifolds in higher dimensions where this de-equivalence conjecture is just known. Yes, it will be. That's not a result of mine, but that's true. Yeah. Okay. So the method here is the methods are equivariant geometry. The methods use equivariant geometry. Okay. So what I'd like to do in the second half of the talk, although it's going to be now the last third of the talk, I'm going to tell you a little bit, not exactly about the proof of this theorem, because this is quite complicated. Maybe at the very end, if I have a little bit of time, I'll tell you how this proof works. But I'll tell you about examples that are already very interesting in the local version of this conjecture.
There's no reason why this new thing is also one of these things.
Well, it's actually, this new thing will be a moduli space of Bridgen semistable objects on the K3 surface for some Bridgen semistability condition.
Do you use
so
that
that's
in the proof?
Yes, that I use. Yeah. So so that's a recent result of Bayer and McCree, that basically they've handled the minimal model program for these varieties, and you have to think about Bridgen semistability conditions to do that.
Is H11 class?
Yeah. It should be. It's a Kähler class. Yeah. It should be an H11. Yeah. Okay. Oops. Well, I'll leave that. So basically, just to sort of so just to review this, Calabi-Yaus are sort of fascinating from the perspective of birational geometry. Okay, their canonical rings are trivial, basically, and then you have this surprising conjecture that actually, even though that's the problem, the cohomology is a birational invariant, and then this de-equivalence conjecture is actually that's just the shadow of some incredibly strong statement, which is that the derived category itself is a birational invariant for Calabi-Yau manifolds, and that's sort of
Is there a Torelli theorem in this setting?
for the K3 for what?
For the K3s, yeah, for these moduli spaces. Is there kind of, you say, you work at the level of the derived category, you get this complete invariance. Can you kind of go down the level of cohomology?
Yeah.
Yeah, we basically result about hyperkähler.
Okay. I'm just.
All right. So basically, I'm going to now walk you through a very simple example, very close to what Mauricio talked about in the last talk, that makes it clear, first of all, why is equivariant geometry useful for studying these birationally equivalent Calabi-Yaus to begin with? And second of all, why is it useful for proving this conjecture? That's sort of the goal for the rest of the talk. So I'm going to now talk about an example. It is the three-dimensional ordinary double point singularity. Or maybe they call this the conifold. I don't know. So basically, I take this. I define a complex variety like this. So I consider it to be the 2 by 2 matrices U, V, W, Z, such that the determinant is equal to 0. And this is a nice smooth manifold away from the origin, where it has a sort of cone point singularity. It lives inside of C to the 4. And basically, I can use equivariant geometry to construct resolutions of this singularity. So what I do is I consider the following. I'm at a V, which I'll call, so it's really a copy of C to the 4, and it maps onto Y. And V consists, the map is given in the following way. So x0, x1, y0, y1 maps to x0, y0, x0, y1, and x1, y0, x1, y1, like this. And so you can check for yourself that this matrix has determinant 0. This map is actually invariant This is invariant for the action of the group C star on this vector space, but not with the usual scaling action, but with a funny action. So this is invariant for the C star action. Which scales the first 2 by t, and the second 2 by, so it's scaling the first 2 by t and scaling the second 2 coordinates by t inverse. So t is an element of C star. And this map is invariant under the C star action. And the idea here is the way you can construct, I use this picture to construct resolutions. So what I'll call my resolution x sub c. It's going to depend on a real parameter. And what this is defined to be equal to is, let me just tell you, phi c inverse of 0 mod u of 1 maps to y. And what is this thing here? Phi sub c is the so-called function. It's the so-called norm squared of the moment map, if you're familiar with this picture. So it's x0, y1. This is equal to, what I do is I take the norm of x0 squared plus the norm of x1 squared minus the norm of y0 squared minus the norm of y1 squared. And then I subtract a constant c and I square it. So the picture here is I have this sort of real analytic function. It's greater than or equal to 0 because it's a real analytic function that depends on a parameter c, and then I've squared it. And I think of this thing as a Morse function, basically. And as a Morse function, it has some global minimum where it's equal to 0, and that's a highly degenerate global minimum. And as long as I choose c generically, in fact, this phi inverse of 0, the global minimum value of this sort of energy functional, will be a manifold, and it will have a free action of the group U1, the unit complex numbers. And so this sits inside this vector space V, I should say. Right? This is a map from V. This is a map from V to R, greater than or equal to 0. Right? And so this actually will be a smooth manifold. It's something with a free action of U1, and I take the quotient. It's a smooth manifold. And this map will actually be 1-to-1, except over the origin, where you get an extra sphere. So that's my claim. That's the resolution, at least topologically. That's the sort of manifold that resolves the singularity. But we're interested in the complex structure. So for that, I just observe. It's a special case of what's called the Kirwan-Ness theorem. So observe that if you define the vectors of the subspace V plus to be the set of points where x0 and x1 are non-zero, so one of these two coordinates is non-zero, and V minus equals the set of points where y0, y1 is not equal to 0, then what you have is that this phi c inverse of 0 modulo u1 is homeomorphic to V plus semistable mod C star if C is bigger than 0, It's homeomorphic to y if c is equal to 0, and it's homeomorphic to v minus semistable mod c star if c is less than 0. And this is called the Kerr-1-Ness theorem. So the point is that this theorem allows me to say, so this is just some submanifold modulo U1 action, but under this homeomorphism, I can identify it with an open subset of the vector space modulo the complexification of U1. This is GIT. And so the thing on the right here has a complex structure, and that's what I'm sort of thinking about. So I just define x plus to be xc for c bigger than 0, and x minus to be xc for c less than 0. OK. So now I'm trying to tell you, so the idea here is that I've constructed two Calabi-Yau manifolds, x plus and x minus, which are birationally equivalent to y, and they're therefore birationally equivalent to each other. And I've constructed them both as orbit spaces for basically the same space. It's this vector space V. It's an orbit space for this, an orbit space for the action of C star on the space V, but I've chosen a different open subset, V plus or V minus. So why is this useful? So this equivariant geometry is useful for constructing these resolutions, but my claim is that it's also useful for proving the de-equivalence conjecture in this case. So the claim is that the claim is the following. It's basically a diagram. So what I can work with, instead of working with vector bundles, I work with equivariant vector bundles. So I have this category. This is what you saw in Romo's talk. If I take dB C star equivariant, so this is the category of complexes of C star equivariant vector bundles, I can restrict it to the derived category of C star equivariant vector bundles on V plus semistable, which is isomorphic. You can just take it from me. This is isomorphic to this, just the usual derived category of complexes of vector bundles on X plus. I can also restrict it to dB C star of V minus semistable, which is isomorphic to dB of x minus. And so the claim is the following. I can find a subcategory in here that I'm going to call M of delta. And what this is going to be is the complexes. This is going to be the complexes built from the subcategory of complexes built from the objects Cn underscore, where by this I mean the equivariant line bundle on V, the C star equivariant line bundle on V, who has weight n. So instead, it's a trivial line bundle, but it has a non-trivial C star action with weight n in the fibers. So these are some line bundles, but only for n in some window. And the window is going to look like delta plus minus 1 to 1. And this is a subcategory of this. And so the claim is that if I consider this subcategory of just complexes built from, if you think about this carefully, let's just say delta is generic. So delta is a generic real number, and I consider only integers in this interval. This is the weirdest way ever to say 2 consecutive integers, but basically it's useful for the general framework or whatever. So you just take these line bundles for 2 consecutive integers, take the subcategory, and the claim is that if I take the subcategory under the restriction functor, these are both equivalences. That's the theorem basically, and this is due to Horry, Herbst, and Page and Siegel. So the claim is that these are equivalences. So the point is that the equivariant category is useful here because it sort of intermediates an equivalence between dB of x minus and dB of x plus. It gives you a way. This theorem says that I can take a complex on x plus, lift it uniquely into the equivariant category, and then restrict it to well, what should I say? Anyway, you take it on one side, you lift it uniquely, and then restrict it, and that's actually an equivalence of categories. And so the equivariant geometry lets you find a sort of intermediate category, which lets you sort of cross this wall. So let me just write that. So you get an equivalence f delta, which maps dB of x plus. First, I unrestrict to m of delta, and then I restrict to dB of x minus. OK? So Yeah, so I'm going to actually declare this to be a theorem template. So I'm going to now sort of flash to a more general GIT situation. So in general GIT, G is a compact Lie group. And it acts on, let's say it acts on it's acting on some projective space times, let's say it acts on P to the n times C to the m in a linear way. And inside of this, I want to have some equivariantly embedded subvariety. Then everything I just said on the previous boards, so there's an energy functional phi sub c. So now C actually lives in the equivariant. Oh, it will live in the second equivariant cohomology of X. And associated to this C, again, it should be a sort of equivariant Kähler class. But associated to the C, I get an energy function. Phi sub c, mapping X to r greater than or equal to 0. So it's again a non-negative sort of energy function of X, and this GIT quotient phi sub c inverse of 0, this zero global minimum of this energy functional in good cases will have a free or almost free action of the compact group G, and this is actually going to be homeomorphic to some open subset modulo the complexification of G. So in other words, basically there's some parameter that lies in a real vector space, C. And as I vary that parameter, basically this energy functional changes. And at certain walls in the parameter space, it undergoes a sort of equivariant surgery.
But what's special about assuming that you have projective space class?
Well, that's just the most general situation in which GIT works, basically, unless you sort of read my thesis or whatever. But that's basically the classical setup, is you have a projective over affine variety. And you can construct a GIT quotient.
Is there any chance that you use it locally? So you could say like variety is local to invariants, or you do blocks along that, and then you know that the categories are equivalent because of this result? Does it work? That you can plug it in locally in space?
Maybe, yeah. In fact, that's the way that the ultimate theorem is proven. But in order to do that, you need some machinery. Yeah. I mean, we could talk. I'm not going to get to that, but we can talk afterwards. Yeah. So this is the sort of setup. Just a general sort of projective over affine complex manifold, and you can construct this GIT quotient. And so sort of the meta theorem, or the sort of meta theorem, I don't know, like proto theorem, whatever. There should be a subcategory depending on a parameter delta, which lies in the same parameter space as C. So just like here, the delta was a real number, and this category depended on the parameter delta. In the general, this delta will be in the same space in which the parameter C lives. And it should be a subcategory of the equivariant derived category of X. And ideally, this thing would map isomorphically so the restriction functor to dB of the GIT quotient, this functor should be an equivalence is an equivalence for C and delta generic. This can't happen in general for all sorts of reasons, but this is sort of a dream thing that this is like a template that you could then use to try to verify. So.
Sure, yeah, you wouldn't need Calabi-Yau.
Yeah, right. So there should be a Calabi-Yau. This should be equivariantly Calabi-Yau. And even then, I can't actually verify this all the time. But maybe it's true all the time. I don't know. Yeah. So.
Or any two birational things.
Yes. Right. Yeah. If the canonical bundle is equivariantly trivial, then you'd expect that all the GIT quotients which are Deligne-Mumford will be derived equivalent. So let me now tell you a theorem. Is it OK if I go a couple minutes over? Because I sort of started a couple minutes late. I don't know. OK. Yeah, OK. OK. So I should say that understanding these equivariant, so the progress over the last like 5 years has been, in my work and the work of Ballard, Favero, and Kutsarkov, some structure theorems to really understand this category of equivariant complexes of equivariant vector bundles. And in some sense, what these theorems, these sort of structure theorems amount to is a way of doing sort of Morse theory for categories. So you can think of a Morse theory as telling you a way to build up the cohomology of a manifold based on the gradient descent flow of some stratification of some Morse function. And in this sense, I can think of this thing as a Morse function. And the structure theorem really tells you how to build up this equivariant category of equivariant complexes out of the strata of the stratification of the gradient descent flow of this sort of Morse function. So there's some sort of deep philosophy relating Morse theory, equivariant Morse theory and equivariant derived categories that sort of underlies and has introduced a lot of new techniques into the subject. Yeah, so let me give you an actual theorem here set up. So I'm going to prove this theorem basically in the following context. So I let G as a compact Lie group, V is a self-dual linear representation, Let's see, I'm going to let delta is going to be a parameter in a real vector space. In this case, what I'm going to do is I'm going to take the weight lattice of the group, take the tensor it with R, and take the violent invariant piece. So M is the weight lattice. And so to this data, there's a purely sort of combinatorial way. To this data, I can actually associate a polytope. So rather than tell you what this polytope is, I'll just show you an example. So if I take the representation T star sim 3 of C2, this is a representation of the group U2. Then the polytope will look something like this. So my weight lattice will be rank 2. There's going to be a line of Weyl symmetry like this. And the thing ends up looking. Oops, OK. So there's some polytope like this. It's symmetric with respect to Weyl symmetry. And there's a shift. So this polytope is delta plus a fixed polytope that's associated to the representation V. So this is sigma V, and I can shift it by some parameter delta. So this is the setup. And you can think of this thing here as exactly that. This is delta plus some polytope in a one-dimensional lattice. And so the theorem is that, so what I should do is I should let M delta, this category. Oh, wow, OK. So I'm just going to replace the old theorem with the new one. So M of delta, this is the category of complexes built from the representations U bar. This is equal to just V times U with the non-trivial action in the fiber direction. So the non-trivial equivariant structure. So I consider complexes built from these particular equivariant vector bundles with U, where the character of U lies inside within this polytope delta plus sigma V. Then the theorem is that this sits inside the category of equivariant vector bundles, GC equivariant vector bundles on V. And the theorem, due to myself and Stephen Sam, is that this restriction functor is an equivalence. So M of delta is equivalent to the derived category of any generic GIT quotient. Basically, there are some hypotheses needed on the self-dual representation, but sort of not necessary for me to do this. So, yeah. So in particular, this is for delta and C generic. And in particular, this leads to derived equivalences between all the so the left-hand side here, m of delta. Oh yeah, so in this picture here, what I'm basically doing is I look at this region in the weight lattice, and I just consider irreps whose character is going to the characters are always going to look something like this, some string of dots. And the character has to just sit inside of this polytope. And if I just take those irreducible representations and just take the vector bundles built out of those, I get some subcategory which is canonically equivalent to the category of any GIT quotient under restriction. And so, so I'm basically sort of out of time. But this leads to, first of all, this leads to derived equivalences between every single GIT quotient here. And in fact, this fits together into a much richer structure. So this leads to, these derived equivalences have relations between them, and it leads to monodromy representations of fundamental groups, like the kind predicted on the level of cohomology. So I mean, I could tell you about that over tea or something later this afternoon if you want to know about it. But this is the basic. So this is the basic input that leads to the theorem on moduli spaces.
There's nothing like a quotient of a vector space by group.
Right. So the theorem there. Well, why don't you ask me a question about that, and then I can answer you. Because I'll end the talk there. But then if there's a question, I can talk about how they're related.
Yeah, because I was sort of